So in this example, consider $1 with interest rate 100% annually, compounded m times per year. And here we just have some numbers. So m is the number of times it's compounded per year. So here we have compounded once per year, and of course $1 would turn to $2 if you earn 100%, or if you earn 100% on $1 in a year. It's compounded once. That would be 1 plus 1, which is 2. M is compounded 10 times per year, 100 times per year, 1,000 times per year, 1,000,000 times per year. So like a daily compounding is somewhere between this 100 and 1,000. So here we're considering up to 1,000,000 times being compounded per year. Now, the left side of this chart is m, the number of times it's compounded. What's the right side of this chart? 1 plus 1 over m to the m. Well, that's the amount in the account after 1 year. And why is that the amount in the account after 1 year? Well, it's 1, the initial, p, well, it's p times 1 plus r over m to the mt. So here p is 1 times 1 plus the rate is 100%, which is 1 over m to the m times 1. A lot of 1s. So basically just set it up so all of these numbers are 1s, except m. Equals just 1 plus 1 over m to the m. So this right side of this chart is going to give us the amount after 1 year given this amount of this number of times that it's compounded in a year. So if you compound it once per year, you get 2 whole dollars at the end. You compound it 10 times per year, at the end you have $2.59 and so on. You compound it 100 times per year, 2.70 and so on. You compound 1,000 times per year, 2.7169239 and so on. You compound it 1,000,000 times per year, it goes only up to 2.7182804 and so on. So this is related to what I was saying before with the example with 4 of them, and the gap between the first two, what was it, annually and quarterly, there was that $91 and some cents, 32 cents gap, and then as the compounding went up to daily, that gap became smaller. And we can see that in general occurs here. Because up here the gap, I mean, it's a relatively small gap. Well, it's a smallish looking gap, 59 cents, but it's relatively large compared to this gap between 1,000 and 1,000,000 times being compounded per year. That changes only by a small fraction of a cent. And we can see, well, maybe I shouldn't say that yet. This number down here possibly looks familiar. Does that number look like a number we've seen before? Well, no, not a number we've seen before. A number you may have seen in another math class. Remark: as m becomes larger, 1 plus 1 over m to the m approaches the number e. E, lowercase e. You may be familiar with it as the base for a natural logarithm. It shows up here. Now, if you have seen calculus before, this would be written as limit as m goes to infinity of 1 plus 1 over m to the m equals e. But the assumption is that you have not seen calculus before. So as the number of compounding times, as the number of times that the money is compounded per year increases, this yield approaches E in this case. And we can use this to describe what is known as continuous compounding. So the compounding we've done so far has been, it's compounding 4 times per year. Compounding 50 billion times per year. It's compounding twice per year. Well, we didn't do an example of twice or 50 billion, but it's compounded a certain number of times per year. But now, with this remark and some calculus, well, you're not going to have to do any of the calculus, but the derivation for the next formula I'm going to write is a Calc 1 problem that maybe I'll ask my Calc 1 students. Continuous compound. Oh, I need to define this before giving you the formula. Oh, that's not compounding. Continuous compound. So I'm gonna so before you write the formula, you should write the definition of continuous compound interest, which I'm going to give you right now. And then I'm going to write the formula over there. So definition. Continuous means that interval, the interval on which we're compounding is getting infinitely small. So we're compounding larger and larger amounts of times per year, but a little more formally. Definition. Continuous compounding, C-O-N-T-I-N-U-O-U-S, compounding, is the method of calculating interest that yields what compound interest tends to toward, not to, T-O-W-A-R-D, with more and more compounding periods. So the compounding periods is like there are 12 per year with monthly compounding. There are 365 compounding periods per year with daily compounding. So continuous compounding is the method of calculating interest that yields what compound interest tends toward with more and more compounding periods. With calculus, that's a little easier to describe. But let's give you the formula. So continuous compound interest formula for principal P at annual interest rate R, compounded, in this case, continuously, because we're getting the continuous compounding formula. So compounded continuously. The balance after T years is A equals P e to the RT, where e is the base of the natural logarithm. What's another place where e is used? Well, remember, so this is not part of this class for the next minute or so. E is actually, one of e's uses is to solve this equation for x. Because e is designed to cancel out with a natural logarithm. E is designed to invert a natural logarithm. And e and the natural log will cancel. That's how all logarithms are designed, to invert an exponential. And exponentials invert logarithms. The same way, very similarly, to solving that equation for x. So, one thing that's very useful, and I don't know if the high schools made as big of a deal of it as you should. I personally decided at some point, I don't know, maybe in undergrad, maybe while tutoring, I decided that these two things look basically the same in my mind. Solving them for x, I should say. They feel basically the same to me. Here, we have to get rid of a natural logarithm. And you do that by doing e to everything. Do that by doing e to everything. E to everything on the left gets rid of everything but the x, and e to the right is 5. Over here, you have to get rid of the 2, so you get rid of the 2 in this case using division or multiplication. Anyway, I'm not going to ask you to solve logarithm equations in this class. Let's do some examples of continuous compounding interest. Let's do a couple. So, given an annual rate of 10% compounded continuously, how much is $1,000 worth after 1 year, after so part A, 1 year, part B, 5 years. That H should be lowercase, but that's okay. So an annual rate of 10% compound continuous, how much is $1,000 worth after 1 year and 5 years? Well, we just use this formula. A equals P, E to the R, T. So in part A, capital A would be P, $1,000, times E to the R. Our R is 0.1, and our time is 1. All of our units are years. Well, our rate is an annual rate, and our time is in years. Again, over here, you want rate and time to be the same units, of course. And this equals, what does it equal? 1,100, 5, and 17. And that's an approximate. In part B, A equals 1,000 times E. R is still 0.1, but here we have times 5 instead, because it's 5 years for part B, and this equals approximately 1648 and 72 cents. So right there, the continuous compounding formulas, I would say it's much easier than the others to deal with, even the simple interest. But do know that in deriving that formula, there is some Calc 1 to derive that formula. And let's do one more example, sort of combining what we've done. Example. Consider $1,000 with an annual interest rate that's not even close to interest. I wrote I-N-T-E-R-E. I need an S-T. Consider $1,000 with an annual interest rate. I should put dollar signs on the money. With an annual interest rate of 5%. How much is in, so consider a $1,000 deposit. The account after 1 year, if interest is compounded A, continuously, B, daily. And I should probably have a question mark after part A over there. Or maybe not, maybe that should be a comma. I don't really know how to format lists like that. I think it's technically supposed to be a comma there, and then, I don't know, whatever. Not a grammar class. Although you should use proper grammar. Very important. I won't compare the importance of using proper grammar to other things. How much is in the account after 1 year if the interest is compounded continuously? Well, again, we use this A equals P e to the RT, which in this case is what? P is 1,000, E is E, R is 5%, 0.05, and T is 1 year. And what does that equal? That is approximately equal to the number I'm about to write. Approximately $1051.27. I like the dollar signs of 2 lines. I don't know the difference between the 1 line and 2 line. I don't know where they came from. But I always like the one with 2 lines for some reason. I could be wrong about that, though. And what about daily compounding? Well, daily doesn't use this P to the RT. It uses the P times 1 plus R over M to the MT. So it's still $1,000 times 1 plus, what's R? Interest rate of 5%. 0.05. What is M? Compounded daily, 365 exactly for this class days in a year. All raised to the M, 365 times T, which is 1, and this is approximately equal to, now what do we suspect this might be approximately equal to? When right before we discussed the continuous compounding, we kind of said that compounding a bunch of times per year doesn't really change much as that number gets very large. I mean, there is a small gap as the money, or as the compounding periods goes up. But you'll notice here, with this example is from the textbook, with this example and these numbers, compounding continuously and compounding daily, rounding to 2 digits at the end, actually resulted in the same net amount in the account. To be, if you extend it out more decimal places, the daily compounding was 26.9 or something. I didn't write it down. 26.8, 26.9 or something. And this other one was 27 point something. So there was a difference in the third decimal place, but if you're actually just thinking about the money you have, compounding continuously and compounding daily led to the same amount of money in the account here. So these formulas, I will not have you memorize these formulas. They will be provided. I won't tell you in the formulas what the letters stand for, so you will have to know that. But definitely try these computations. Definitely also be sure you can put these in your calculator and get the numbers that I'm getting. All of the numbers we've done here, I'm pretty sure are correct, but they're mostly from the textbook. There were 4 or 5 numbers that weren't from the textbook, but I'm pretty sure they were correct. I was careful with checking the calculator I used. But definitely be sure you can put these in a calculator and get these numbers, and definitely be sure you understand the formulas and try the worksheet problems, and well, there's a homework due this week, so let me know if you have any questions.